Okay. Hello and welcome to the New York City Category Theory Seminar. Tonight, whatever. We have Amartya Shekhar Dubey. You'll pronounce it better when you get there.
Oh, that's
We'll
fine.
talk about Unital K-restricted infinity-operads. This is our first talk of this semester, and welcome.
Yeah, first of all, thanks y'all for being here. And so yeah, I'm Amartya, or you can also call me Ash. So at the moment, I'm doing my master's thesis in Utrecht University with Leonard Maya. And at the moment, I was supposed to be in Utrecht, but I'm in India, as you might see from the unusual time. So so here's what we're gonna do. So
Do you have to do with Icky Berdeg there in Utrecht, or is he
yes,
in?
that's right. Yeah, he
Okay.
is in Utrecht as well.
All
That's
right.
right. Right. In fact, we recently met over the East. Like there was this European autumn uh, topology school there. But yeah, so let's get to the math. So here's what we're gonna do. So I'm gonna be honest. Like I did not have like plans to prepare like slides for this talk. Initially, I was thinking that I would just do a tablet talk. So what I ended up doing is that I had slides for like a 30-minute talk that I prepared. So what I ended up doing is that I trimmed some parts of it, and then we're gonna go. So we're gonna have a couple of parts. The first part's basically a bunch of definitions and some stuff, which is part one, and the second part's where the real math is, and that's for that I'm gonna use my tablet. So here we go. Okay, so this is the outline. So an intro to the intro, like so basically, just gonna tell you what infinity operads are. I mean, just remind you, and then we're gonna see why like this is like an interesting thing. Why it's interesting to consider like these restrictive unital infinity operads, and then so yeah, right. We'll see what dendroidal trees are. So we're basically so like as you might understand, so this is we are basically translating whatever Szysinski, Moidike, and Weiss do to the restricted setting, right? So let's begin. So here's the part one. So I'm going to start from what an operad is. I mean, just to remind y'all. So in Jim Stashov's words, an operad is an abstraction for a family of composable functions for n variables with various n useful for the bookkeeping and applications of such families. So here's like an informal definition. I'm not going for a formal definition, right? So an operad in C. So you have these objects which come equipped with these maps, right? And oops, and there's like an identity element, and so we are considering symmetric colored operads, by the way. Um, right. Oops. Right, and then you have an action of sigma n on each Cn, and then you have some coherences that relate this action to some other structure, like which are like these compatibility conditions. So here's an example. So it's like the endomorphism operad, basically defined for vector space V. So this NVN are like maps like Helm sets from Vn to N, and where you have composition, which is defined as follows. So this F compose F sort JG. So it is the map that is given by using the output of G as the Jth input of F. Straightforward enough. So that's what operads are. And I'm gonna see like what infinity operads are. And I'm not going through like the whole construction. I'm just gonna give you an idea. Like I just gonna tell you what it is. Like there's loads and loads. Like there's I think NLab says there's like 5 or 6 models. I don't know. But so there are many equivalent models for infinity operads. The one that we care about is Szysinski-Moiré-Weiss model. So what is a dendroidal set? It is a presheaf from the tree category. And yeah, at some point, yeah, we're going to see what the tree category is. For the dendroidal model, so here's the slogan. Here's all that you want to know. So simplicial sets are to infinity categories. Dendroidal sets are to infinity operads. So you have JL model structures, and the cofabulate objects are quasi-categories. Similarly, you have like this model structure and dendroidal sets, and the cofabulate objects are the quasi-operads. So that was the introduction to the introduction that we cared about. And now here's the actual introduction. So Lurie basically, so this gives us a Stashev level understanding of associativity in the formalism of infinity operads. So what does that mean? So he constructs converging filtration that looks like the following. So what are these NUs? These NUs, so this NU means non-unital. So this ANU infinity is the non-unital associative infinity operad. And this ANU sub k is parametrizes multiplications that are associative up to k inputs. Right.
Oh, hold on. Just what are the ANUs? Oh, back up. Yeah.
These are like non-unital associative operads, infinity, and NUK is, yes, please feel free to stop me at any point if I'm going too fast or whatever. So A and UK that parameterizes multiplications that are associative up to k inputs.
Right. So when you write the A here, that looks suggestive of an A infinity algebra where, but now with multiple inputs, because in the infinity
Absolutely.
algebra, we just got binary operations that have associators. Now you're just doing multiple ones. Okay.
Okay.
All right, cool. So, right, so there's a sense in which we think of ANUK as the k arity restriction of ANU infinity. So what does that mean? So this map that you have from ANUK to ANU infinity, this induces an equivalence of n-ary morphism spaces for n less than equal to k, and then the n-ary morphism space NUK n for n greater than k is generated by these less than equal to k morphisms in a suitable sense. So this basically motivates the natural notion of a k-restricted infinity operad where we only consider n-ary morphism spaces for n less than equal to k. So so you basically think about them as k-arity skeletons of infinity operads. I mean, that's supposed to be our motto. And like throughout these slides, like what we'll basically see the definition. We'll try to define what give a model for these unital. And why do we need unital? We'll also talk about that towards the end. And what I mean by unital as well. Right? So Hertz basically constructed the infinity category of non-unital k-restricted infinity operads and proved the following, that the natural restriction functor that you have, it has fully faithful left and right adjoints. And we are basically interested in unital versions of k-restricted infinity operads. So what do I mean by unital? So it basically means like for O, like mul O, phi x is contractible. So that is what I mean by unital. So, right, so we're just gonna see the main theorem that again, I'll see what I can do with the proofs. So my goal here is to actually prove the left adjoint statement in detail. I'll try that, and for the right adjoint statement, that'll depend on how much time I have towards the end of the talk. So this is the theorem that we have, and we'll see this later. So for 1 less than equal to k less than equal to j less than equal to infinity, this functor admits fully faithful left and right adjoints, which moreover are given by left and right conic extensions along this inclusion. So that basically was the sort of introduction that we needed. Now we're going to see what this. Now there's going to be loads of definitions that we have, so it might be a bit boring. So what is a dendroidal tree? A finite rooted tree is, so first of all, a finite rooted tree, it is just a poset. It says that you have a minimal element, and for every x in T, the subposet T less than equal to x consists of elements less than x. It's linearly ordered. So that's what I mean by finitely rooted tree. And when you say dendroidal tree, it's just like T with the set of leaves, which are the subset of maximal elements. So we just denote them instead of saying TL, so we're just going to say T, right, for brevity. So that's what a dendroidal tree is. Now, so if sigma is a category of dendroidal trees with objects and trees in the following, then right. So this is the sigma that we solved for. So like definition. And now, so this is something that's important. So a tree is closed if the set of leaves is empty. And the full subcategory that consists of these closed trees, we're going to denote it by sigma c. Right. So it is pretty straightforward to see. I mean, I'm not, yeah, I don't have, yeah, maybe you can talk about this later. That sigma c can be explicitly thought as a category with objects being finite rooted trees and morphisms being order preserving maps, preserving independence. I mean, that's pretty standard exercise. And right, so here's the proposition. So sigma C is the category of mu local objects, where and for any t in sigma C, the unit t to tc is localization relative to mu. And what is mu? This unique map from eta to co, where eta is like the dendroidal tree with one edge, and the cn's are corollas, and that's pretty standard notation.
Oh, well, no, one second, one second. The corollas are just they're connected to the tree, but they're not connected to any other. They're just connected to one limb. So they're leaves, but only by one node.
Yeah, that's right.
Mhm. And what does it mean? Back up for a second. The unital. What does it mean about object about what is the unital property that it's connected? What is that? What's the intuition behind that? I
Sorry,
mean,
what
for
was that?
example, in Ham Vn to V, isn't it always
Okay.
vector space is always connected or something? I mean,
Like, what statement are we talking about here?
your definition of unital,
Okay. Oh, okay. All right. And okay, so right, so here.
right?
Uh, right. And what was the question again? Sorry.
Contractible. What is how does one think about that? I mean, I know what contractible means of a topological space, but in terms of operations, what do you think of, how does one think of that?
Well, I mean, it's gonna make more sense if you like, try to draw it down. Like it's very combinatorial, I guess. Like in this situation, at least, like for this like story. But right. So how do I say it out? Uh, Okay,
Okay,
this
it's
actually comes up later as well at some point. So maybe I'll answer that
okay,
question at that
okay,
point, I guess. Or not. If not, then I'll maybe talk more about it when I'm on my tablet, if that's okay.
okay, okay.
Cool. Sorry about that. Right. So now we're interested in looking at factorization systems on this omega C. So these are classes of morphisms of interest. So basically, start off with the morphism in sigma C. Then the morphism is said to be rooted if it takes the root of t to the root of t dash. And it is said to be a subtree inclusion if it's injective and the image of t is a subtree of t dash. And it is said to be max surjective if for every edge e dash in t dash there exists an edge e in E such that f of e is greater than or equal to e dash. So these are our three classes of morphisms that we're going to see later. Uh, right. So we call rooted max surjective maps active and subtree inclusions inert. So that's something that's important because these classes, like those classes of morphisms, like of max surjective and rooted subtree inclusions, these form a factorization system on sigma C. On yeah, right, sigma C. So how do you see that? I mean, so you can see the uniqueness part's not hard. So if you start with a map G from T to T double dash, then suppose T dash is the rooted subtree of T double dash that consists of like these edges such that like the way we define it actually, like there exists an edge E in T such that F is greater than or equal to E dash. And G basically factors through T dash and then by construction, by the first map will be max surjective. So it's fairly straightforward to check.
It's like a density
It's
condition that the T prime is dense or something like that. T is what? How does one think of these
yeah
things? Is it dense or is it covers everything or it covers some things?
I think I should have wrote that. Should be dense.
It's a way of saying it's like a maximal
Hmm.
subtree of a graph or something like that.
Right, like that. Yeah, more or less.
Okay.
Okay, so moving on. So similarly, we have like rooted max surjective maps and subtree inclusion. These form a factorization system. And so therefore, like if you take any morphism in sigma C, you have this unique factorization like this. This F1 is a rooted max rejective, F2 is max rejective, and F3 is rooted subtree inclusion. Right. So what do I mean when I say a tree is k-dendroidal? So that basically that just means that it is a dendroidal tree, and like every edge has valence less than equal to k. So this is like a notation that we're going to use. So this is like the full subcategory of sigma, and similarly, like we have this subscript less than equal to k that consists of these k-dendroidal stuff, right? So this is something that we're going to see later, that pops up later. So you have this localization function. This restricts to a localization, like the following. Like if you move on to the close subcategory of these k-dendroidal things, then you also have this. Right. Okay. Moving on. So here's the lemma. So you start off with a map in sigma. Then if the map is subtree inclusion and K is a k-dendroidal tree, then so is K dash. Right. Then
Where's K? Oh, K by K
K,
comma.
K, yeah,
Okay,
right.
yeah. Hold
Yeah,
on. So it's
yeah.
a
There's a typo. There's a
if F is
typo.
a
Yeah.
subtree inclusion and K is a K, then K is also a
Then there's like
so
typos.
K comma K
Yeah, yeah.
prime. Okay.
K prime. Yeah.
If it's maxly subtree, then K is also okay. Okay.
Yeah. Sorry about the typo.
Yeah, it's okay.
Uh,
Now the K ganja out of the
okay.
last two
Yeah.
props is the following value. Okay.
So similar to the factorization systems that we had seen in this sigma C in the category sigma C, we also have like these factorization systems and sigma C less than equal to K, like max rejected maps and rooted subtree inclusions and rooted max rejected maps and subtree inclusions. So yeah, the goal of this section. So this is like the last part of this of the slides. But I'll try to define what a unital k-restricted infinity operator is. So what we are going to do is we are going to use this Segal presheaf model. So this build shot work by Clark Bowick and Shu Hoxing Hertz. So we'll see what I mean. So first, we start off defining some things like again, so define a subcategory of sigma over T, which consists of morphisms, such that like x from x to T, so that x is either eta or like a corolla, and F is a subtree inclusion. Furthermore, if X is an n corolla with root Z, then F Z also has valence n, right? So now this model that I was talking about. So first we're going to see what a Segal presheaf is. Right, so you started the presheaf on Mega, so then it is a Segal presheaf if for all trees T, this map that you have, and you're taking limits over. So we just defined this category, if you remember. So this basically is a subcategory for the sigma over T, consists of these morphisms. So if you take the limit x, so this is an equivalence. So that is basically your definition for a single presheaf. So now
So
we'll
basically, F of T is nicely made up of its parts,
right. That's the way you picture it, right?
right?
Right. So now we will basically we'll generalize this to SQL presheaps. And so this is like the core idea that we are generalizing this to sigma c less than equal to k. So right. So here's our definition. So we started the presheaf on sigma c less than equal to k. Then it is said to be a SQL presheaf if for every closed k-dendroidal tree T, this map right here, similar to this one, is an equivalence. Remember, so here we are taking the closure. So that is something that you should remember.
Okay, why does it have X to the C? What is the C for on top?
That stands for the closure. We're taking the closure.
Uh, so so f of t here is not equal to the sum of its parts,
Yeah, it's
but it's
not
equal to the closure of the sum of
sum of its
it's
parts.
equal to the sum of the closure of its parts. Okay.
Right.
And the reason why that's important is because the k's um because these are smaller things. Oh, 1 second. Okay. Okay. The omega on top is just a dendral something tree.
Sorry, what?
The on the top line, F is a presheaf of omega. That what is omega
Yeah.
there?
So this oh
No, the
here,
top,
like the
yeah,
first.
that one without the C in the list then, right? What
Yeah, that is just a general category.
just any dendral kind of, okay, fine.
Yeah,
And so here
that
you're
is
talking
fine.
about the F is a presheaf on
Closed ones with
right. Okay, fine.
restricted, right? Uh, so let's denote the full subcategory of Segal presheaves by CL like SEGC. C. So, so here's a remark. So if you consider a map of Segal presheaves on sigma CK, it follows from the Segal condition that F is an equivalence if and only if this map that you have, it is an equivalence for. So this is essential in the proofs that we'll see this later. This is something that pops up later in the proofs, like for all these like i's less than equal to k.
Now, what's the bar on top of the CIs?
Sorry, what? Oh, the CIs.
What's the bar
That
on
is
top of them?
that is the closure. Just closure. What are you
Oh,
trying
so you
to?
don't want to use the word C again.
Yeah, because it sees
Yeah, okay, I
i's.
understand.
Sorry. Yeah, I should have said that. Right. So yeah, now we want to relate Siegel presheaves on sigma and sigma c. So the pullback functor is so here's a proposition. So the pullback functor that you have, so this preserves Siegel presheaves. So and then the functor induced on this Siegel presheaves on this subcategory of Siegel presheaves is fully faithful. And the image of this functor, this consists of Segal presheaves on sigma, yeah, so it's like this is an equivalence. So this is essential. We'll see. Right. So basically, we'll see a criteria that we actually use for the Segal condition and the proofs. So I mean, this is the kind of a walkway around that we're doing. So you start with the tree, then row tree T and an edge. Then you define the upper subtree of T with root E as follows. And similarly, you define the lower subtree of T with leaf E as follows. All right. So this T greater than E, we're denoting that by VE. Right. So now, so how am I doing on time? 30 minutes, okay.
You're about halfway through. What's TFAE?
Yeah, my bad. So you started the pre-sheaf on Omega.
Mm-hmm.
Yeah, I'm sorry. Yeah, I've been saying Omega and Sigma interchangeably, so
It's
I'm
okay.
sorry about that. So then the following are equivalent. So that's like yeah, that's like
Oh,
something that I
okay.
do quite often. So this is like an equivalent condition for like Siegel pre-sheaves. So it is a Siegel pre-sheaf, and for every tree, general tree T and an inner edge E, it's mapped that you have. So this is like an equivalence. And there's for every TT and a non-maximal edge E naught of T, this map. So this is something that make more sense if you actually work it out. It's not that hard to prove. So right, so this is an equivalence. So this gives us like two equivalent ways, and these are gonna pop out, like especially the second one in our proofs of the left adjoint statement that I intend to do. We'll see how that goes. And here's like another version, like this is like the fourth equivalent condition that for every T this map is an equivalence. Right, now we're going to move to, translate this to the dendroidal setting. So you start with the Segal presheaf, k-dendroidal setting, I mean. You start with the presheaf on omega c less than equal to k, then the following are equivalent. You have like similar conditions. So here you're taking the closure as well. So as you might see, right. So yeah, that is an equivalence, and like similar to the last proposition, we have like similar statements. Right. So now we can define complete Segal presheaves in the closed k-dendroidal setting. So you fix k and j, and where C is like one of these categories, and a Segal presheaf on C is said to be complete. That Segal space is a complete Segal space in the sets of rest, and there's something that I don't want to get into the details of right now, given the time that I have. But that's what I mean when I say complete presheaf infinity categories. So note that if you have if like R is an inclusion between the simplex category and the dendroidal category, right? Which we by abuse of notation we use to denote this, as well as like its factorization through this category, like sigma c less than equal to k. Then right, so that's something that we should keep in mind. And so we denote our full subcategory of complete Segal presheaves by just adding this subscript CPL with Segal presheaves. So following Joyal tyranny, the tyranny proves so that C as this complete Segal presheaves as like equivalent to cat. Right. So here's a remark. So these functors, I start K and this functor. So these preserve and detect complete objects. And we're going to denote the functors and complete superficies by the same symbols as well. So here's like the central theorem that we build on. So this uses, as I'd mentioned, like this follows Baalbek, Schuhawks, and Hertz. So you have an equivalence of infinity-operads. So this is something that they prove that if you take the single presheaves, then you're going to get the category of infinity-operads. So under this equivalence, this eta corresponds to the infinity-operad trait, which was like, as you might remember, A n U0, and the n corolla, this corresponds to free over Cn. Right. So yeah, so again, so this is something that I'll probably get to like when I'm like started writing. So just recall what it means when for an operad to be unital. So we denote the full subcategory of op, which consists of unital infinity operads by op u n. And then basically the last term that we saw, so you have a restriction. So this is important that this op u n is going to complete Segal presheaves over for omega c. So here's the definition. So following the last corollary, we have the following definition for k-restricted unital infinity operads. A k-restricted infinity operad is a complete Segal presheaf on omega c less than or equal to k. And right, so this is so we denote the subcategory of complete Segal. We denote the category of complete Segal presheaves over omega c less than or equal to k by this like op un less than or equal to k, and this k, this is basically the functor that you have that you're gonna get, like the one that we saw before, right? So now suppose f is a unital k restricted infinity operad, then we refer to fc0 bar as its space of colors. Additionally, given 1 less than equal to n less than equal to k, and the colors x1 to xn y in F. So this we use this notation for the fiber product. So that is important. Again, so here's your mark. So you start with a map of unital k restricted infinity operads, then the following are equivalent. It is an equivalence, and for any map k, this map that you have, It's an equivalence. And the third condition is the induced map on colors is an equivalence. Furthermore, for any one less than equal to n less than equal to k and colors is this induced map which we have. So this is an equivalence too. So this gives us like two equivalent conditions. So now pulling back like complete Segal presheaves along this R, so you get a functor like this. So this is a model. So this, and we know that complete Segal presheaves over delta is just cat infinity. So it basically takes a unital K-restricted infinity-operad to the underlying infinity category, right? So now I'll stop my screen sharing and we'll move to my tablet where I'll try to prove something. So I'll just take a minute.
Am I audible? Just checking.
I hear you. We hear you.
So share my screen. All right. So the adjoints. Right. So this is where the interesting stuff happens. So given uh 1 less than equal to k less than equal to j, we have an adjunction. Right. This is ik star. So where
This is
this
sheafification. What is this?
so these are presheaves. So you have an
Oh,
adjunction.
on different things because so one is less than U. Is that less than C? And
Less
what
than
is?
j. I'm sorry. This is less than equal to k, this is less than equal to j, and you start
Oh,
with.
I see. So you have different arities going on here.
Yes, that's right.
There's an inclusion, and what's the functor going the other way? Actually,
This ik, a star, a star. So ik is basically the, okay, I was about to write that.
okay,
So,
sorry.
so this L con k, so this is like the left con extension along this inclusion, right? And what we want to show is this L con k preserves complete Segal objects. Uh, thus, restricting to a fully faithful left adjoint. So fully faithful left adjoint. It's kind of running short on time. So I'm just trying to keep it short. Right. So this is yes. So this will restrict this fully faithful left adjoint to the restriction functor, which is what we care about. So first we'll state a few things. So my goal here is to prove the statement for the left adjoint and state the statement for the right adjoint because it's like way more involved. Right. So right. So some notation. So you start with a functor between infinity categories and d is in t. So then you're going to denote ct over uh, denotes the fiber product. Right. And yeah, this is like the under category. So similarly, C. So this denotes the fiber product. This is like the over category. Uh, so here's the definition. So you start with a closed tree and k is greater than equal to 1. Then I'm going to define this t or x. So this is like the full subcategory of this whose objects are rooted max surjective morphisms, and from T to closed, uh, yeah, I'm just going to write it, closed k-dendroidal strings. So here's the lemma that I'm going to use in the proof. So given k greater than equal to 1, okay, and T is a closed tree, so you have an adjunction. Mm, fact. Right. Okay. Let's see. So what is the, oops, we're gonna have to start another one. Yes. Oops, not bad. I'll have to figure out how do I add a page to this. Uh, sorry about this. Jesus.
What's about me? You can't. It's only one page.
Uh, Slightly more than a page. So maybe I'll start afresh. Um, ah, not bad. There you go. Yeah, sorry about that. Mm, cool. So, okay, let's write this again. So, add this junction. What's the- Right. And so, what is the left adjoint? The left adjoint is basically the canonical inclusion, and right adjoint is you're basically taking the factorization with respect to the this factorization system that we saw, rooted max surjective, perhaps, and subtree inclusions, right, that we saw. Right, so here's the lemma. So this is important. And okay, so something more that we need. Right, so you start with a map of closed trees, to closed trees, and then you consider this composite. T dash upper star, and then you take the fact. Scalan. So what does it do? So you basically start with the rooted max surjective map. So it's got to take it to the factorization of, uh, sorry. So this is just from T to X. So this is like the composite, right? And yeah, X is like the root factorization of the composite. Uh, T goes to T dash, and dash. All right, so X is, so it is like the factorization of this. Right. So now, uh, I think. Okay, so consider this. So we want to see how, like the goal for this is to see how this behaves with respect to cutting a tree along an edge. So that's the goal. And so you start with a closed tree, T, and E an internal edge, T. Then, like, remember we had defined these. So here we are taking the closure, remember. Now, so let's define these inclusion maps. So I don't know if we use this notation in the paper or further on. I think we use this. And so these are inclusions. And suppose we have a max surjective map, CT to X, that takes this E to X in X, lowercase x, so E to X. Then basically this in ER max of this G to T to X is basically G X greater than X. And uh, another thing, so let me move to another slide. Yeah, I'm extremely sorry about this. Right, and this inc ER max G from T to X is closure. So, like this also has an inverse construction. Like you can get an inverse, but uh, so you basically start with two rooted max surjective maps. Okay, let me write it down. So I have 11 minutes, so you can write it down. So you start with something like this. So this is like two max, okay, also rooted max surjective maps, G, E, and G lowercase e. This is x1, G to x2. And you can basically build this. So this is inverse. You can basically build this tree by gluing the root of x1 to the outer edge. So glue root of x1 to the outer edge of x2, right? And these GE and GE, so these lowercase e, G subscript e and G superscript e, so these induce a rooted max surjective map, T2, right? So we get a functor that we call glue, E max. Then here we take the closure to TR max, right? So from this, like from all our like short discussion, we have this lemma that these inclusion maps and max. So these, um, so okay. So first T is a closed tree, and E is an internal edge. That this functor, T R I greater than E R max times this. I can just So this is an equivalence, is an equivalent with inverse is glue. This is what I want to say. Right, so now we're going to prove the main theorem. Right, it's a proposition. So the left con extension, so how much? Okay, preserves complete Segal presheaves. All right, proof sketch rather. So first we're going to prove that this L con K, this preserves Segal presheaves. So you start with the Segal presheaf. Then, so this is like one of the equivalent statements of presheaf being a Segal presheaf. It suffices to prove the following. So you have a k-dendroidal tree T for any k-dendroidal tree, which is also closed, and E an internal edge of T. This map is an equivalence. Just remember these were like one of the equivalent statements that we had. Greater than equal to J. Oh, right. So okay. So how do we move forward? So right. So we have that we can write this K of T is the following. So I'm gonna skip some steps, but we can talk about it. First, I want to have the proof written down. Right. So so where does this come from? So this is because so this is pretty easy because like you have this inclusion uh tr max CR. So this is co-initial. So the so this is like from this co-limit to L con K of f of t. This is basically this is an equivalence because this is co-initial. And okay, so here's the first step, and now second step. Take co-limit x to. So it gets a bit messy here. So you can follow around the paper if you want. Times R max. This is like this is something where we are using this lemma that we saw, where we are basically like this inverse, this gluing thing that we saw. So that's where this comes from. Then uh, so it is the same. So I'm gonna just leave it the way it is. Okay, and more steps. Uh, right. Uh, so here we are, at some point, like in this proof, we are basically going to use the fact that the colimits are universal in X S, right? So so that's why you can commute colimits with fiber products. So that is something that we're going to use. C okay. Search. Search. This thing here. And then, yeah, just a bit of rearranging colimits of our products. You're going to get skipping some stuff here. This is what you're going to get. Right. So now the only thing that we want to show is that this Alcon K preserves complete Segal presheaves. So so that's not hard because like so you have this map R from delta to so this factors through. So remember you started with this factors through, and then you also have Alcon K of F. It's just F for any presheaf, and so I mean it follows. So here's the left adjoint. So define this to be the okay. So this is the functor. So this is complete Segal presheaves con K. Okay. Right. So that gives us like the so this so we have this adjunction. We're gonna get this adjunction. Furthermore, the left adjoint is fully faithful. So what's important? So I'm seeing that I'm running out of time. So I'm just gonna state a few things. So basically get uh, a colimit description of the multi-spaces of F. So a corollary would be, so F is a unital K restrict infinity operad, then okay, Cn. So this is basically just a colimit. Search op X. So that basically means that the space of n aromorphisms of F or n aromorphisms of Lk of F is the space of all possibly n aromorphisms, L aromorphisms that can be created by less than k aromorphisms of in F. Right? So and similarly, you have the right adjoint statement as well. And then there's a few examples that you can find in the note. But since I started 5 minutes late, I'll just take an extra few minutes to write the right adjoint statement. Just a statement.
Okay.
Right. So this is like all analogous. I'm just going to write the statement, but it's a bit more subtle, actually. So again, we start with j less than equal to, oops. Okay, less than equal to. So we have an adjunction. Choose. Oops. This is J. This is K. R con K. And this R con K preserves this. Okay, firstly, this R con K is the so it is the right con extension along this inclusion, and It preserves complete Segal objects, and then this restricts, therefore, to this fully faithful right adjoint to this restriction functor. So, okay. So what we get in the end? Uh, so I'll see if I have time for this. Okay, but anyways. So yeah, just to summarize, the last thing that I'm gonna write. So you get a co-filtration for A infinity like this, using all these things that we've done so far. One by infinity, and this is just infinity. Yeah, so that's all I had to say. Thanks everyone for listening. Albeit,
Okay, thank you very much. It's a world I'm not familiar with, but it was very interesting. Any questions? Any discussion? Any unhappiness? Any? All right. Anyways, so thank you very much, and I'm going to put it up in an hour or so. Okay.
okay.
Okay. Good luck. Good luck
Thank
with
you.
your PhD.
Thank you. Thanks a lot.
Okay. 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 Take care.